Hey everyone, Miss Butler here. I have a video for you on an introduction to acids and bases. This is probably the first video if you're in honors chem or regular chem. So there may be a couple of times I talk about specific things for one class or the other, but this video is pretty good for both classes, both levels. So we're going to start with molarity and dilution. I'm just going to do one problem here, but you have already seen this. So if this does not go well or you need a refresher, look back at the last couple of assignments or reach out to your teacher to get some help on molarity and dilutions. All right, so if 2.5 moles of HCl, so we have 2.5 moles, it's dissolved in 300 milliliters. What is the concentration? So remember, concentration is molarity. And we know that molarity is equal to my moles divided by my volume, which is liters. So if we're looking for capital M, the first thing is I see that they gave me my volume as 300 milliliters. That's the same as 0.3000 liters. So to go from milliliters to liters, you move the decimal 3 spots or divide by 1,000. So now we should be able to calculate. So big M is equal to my moles, 2.5, divided by my liters, 0.300. When I plug that guy in my calculator, 2.5 divided by 0.3, I get 8.3 molar or 8.3 moles per liter. Same thing. So now they want to know what is the new concentration if 12 milliliters of that 8.3 molar is diluted to a new total volume. So anytime there's a dilution, that's M1 times V1 equals M2 times V2. So I have my M1 at 8.3 molar. We found that in the last problem. They are taking 12 milliliters of it. I want to know my new concentration, so I want to know my M2, and I have a new total volume after the dilution. They add some water of 250 milliliters. So this is just pretty simple multiplication. We're going to take 8.3 M1 times the V1, 12.0, and that equals M2, what we're looking for, times 250. When I take 8.3 times 12, I get 99.6, and that equals 250 times M2. Divide both sides by 250, and we get M2 is equal to 0.398 molar or mole per liter. So hopefully that was a good refresher. Go back, watch the video on molarity and concentration if you need help with dilutions or calculating molarity. So now that we're in the acid-base unit, we need to be able to define what an acid is and what a base is. There are lots and lots of definitions out there on how to define what an acid is and what a base is, but for our class this year, we're going to look at the Bronsted-Lowry definition. In this definition, we're going to think of the H plus ion as a proton, and so in that situation, an acid is known as a proton donator, so it is giving away H pluses. A base is a proton acceptor. So here's an example. I have an acid, HCl, and a base, OH minus. If an acid donates a proton, that means it's going to give this H plus, and a base, it takes the proton, so this OH is going to take it. So if we take this H plus and we bring it over here, that is going to create H2O. Let me rewrite that real quick. What if I wrote this as HOH? This H came from here. Oh, sorry about that. And this OH is right there. So we took the H from here, we added it to the OH, we made HOH, which can be rewritten as H2O, and then we have our Cl minus. The general net ionic equation, and I know regular chem, you don't know what net ionic means. It means like the simplified version of a reaction. For acid reacting with a base is H plus, acid, plus OH minus base, always makes water, and we're going to talk about those in a second. So I mentioned we were going to talk about some reactions. Let's look at those. This unit, we're going to see two types of acid-base reactions. The first is called neutralization. This is where I add an acid with a base and it creates water. We'll see sometimes there's another product as well, but the main idea is an acid and a base will neutralize each other and it becomes neutralized in the form of water. Okay? So that's why if I spill an acid on something, I'm gonna sprinkle some base on there to try to neutralize it and create water, which is safe. The other type of reaction we're going to look at is called a dissociation reaction, and this is where we just take an acid and put it in water and see what happens, or we take a base and we put it in water and see what happens. So I want to talk about that first type of reaction first, neutralization. This is the one where we add the acid with the base. So here's kind of my first go at this. Potassium hydroxide solution. So we know potassium is K with a 1+ charge. Hydroxide is a polyatomic with a -1 charge. We crisscross. One goes here, one goes here, so we're left with KOH, right? One of each, and you can keep this in parentheses if you would like. And that is aqueous because it said solution. That means dissolved in water, right? It is titrated. We will learn more about titrations later, but that means it is reacted with 0.1 molar nitric acid. So nitric acid is hydrogen with the nitrate polyatomic. And we may have time this school year to look over naming and where these names come from. If not, a weird name like that would be given to you, or the formula would be given to you. So we crisscross 1 and 1, and so that gives us HNO3. And that is aqueous. So there's my two reactants. This one is the acid because it has the H+ to donate. This one is the base. It's going to accept the H+. And this to me looks just like a double replacement. I know that we're always going to make water, right? So pull out the water first. So we pull out HOH. So this H reacts with this OH. That's our water, and that's a liquid. Plus, now we crisscross the other two things. So we have K, which is +1, and NO3, which is -1. We crisscross, and I get KNO3, and that is aqueous, meaning dissolved in water. If you are in regular chem, I want you to always assume that the other piece besides water is aqueous. If you're in honors chem, I want you to use your solubility rules, and we know that NO3 is always dissolved in water, always aqueous. So now, this would be, and this is balanced, right? There's one of everything, one OH, one OH, one H here, one H here, one NO3 group, NO3, K and K. So this is balanced. If you are in regular chem, you are done, right? We have an acid plus a base makes water, and then I told you there might be another thing. If you are in honors chem, we are going to do the net ionic equation. So we're going to break anything that is aqueous down. So we have K plus aqueous plus OH minus aqueous plus H plus aqueous plus NO3 minus aqueous. So I just broke these guys back down into those ions that we used to crisscross. That makes H2O, we do not break apart liquids, plus aqueous breaks apart, K plus NO3 minus. So there's my complete ionic equation. Sorry, that's aqueous. We're going to cancel out spectators, K plus aqueous, NO3 aqueous, NO3 aqueous, and now you see the leftovers for the net ionic OH minus plus H plus makes H2O liquid. So again, if you are in regular chem, this can be your correct answer. I would love if you can start to figure out how I went from here to here and then to here, but really that stuff in yellow is more for honors. So just kind of a breakdown there. All right, rubidium hydroxide, we got a crisscross. RB is 1+ from my periodic table. Hydroxide is OH minus 1. When we crisscross, we get one of each. So RB, OH, aqueous, plus, and that's aqueous because I said solution, it's added to acetic acid. Well, acetic acid is just an H+ with the acetate polyatomic ion. And again, if this were an assignment, I would probably give you those formulas right now until we go over naming for acids in particular. For bases, usually you can crisscross. So then we crisscross 1 and 1, so I get HC2H3O2. So this is my base, and I'm actually going to clarify this is a strong base, and this is my acid, and I'm going to clarify this is considered a weak acid. I'm going to talk about those things in a second. Oh, and that's a solution, aqueous. On the last problem, both of the things we dealt with were strong. It was a strong acid and a strong base. But in this one of them's weak, so we're going to look at that in a second. But we know we always make water, so we always make HOH as a liquid, or H2O, right? That H and that OH. And my other product is the other two leftover things, and we have to crisscross. So RB is 1 plus, acetate is C2H3O2 with a -1. So when I crisscross, I get one of each. RB, oops, yikes, let's try that again. C2H3O2, and that is aqueous based off solubility rules, honors, or because I told you to make the second thing aqueous, regular chem. All right, so now we're going to do, so regular chem, I think we're balanced. I picked another one that was all 1-to-1, so we don't have to balance. You are done. Honors chem, let's do our full equation. I'm going to break apart RB and this weak acid, even though it says aqueous, I am going to leave it together because of this right here. We always leave H2O because it's a liquid, and this aqueous we will break apart based off solubility rules. Spectator ions, I can cross off RB1 plus, and that's it, because I cannot cross this guy off this time because it's part of this guy that did not break apart. So when I write my net ionic, I have OH minus aqueous plus HC2H3O2 aqueous, no charge there because we didn't break it apart, H2O liquid plus C2H3O2 minus aqueous. There's my net ionic equation for honors. So honors, I expect all three. Regular chem, you're just working on this first one. So real quick for honors, if we're going from the full equation to the net ionic equation, if something is aqueous, you are going to follow solubility rules. Or if it is a strong acid or a strong base, you will break it apart. So if it's something that is soluble, it is aqueous, you break it apart into ions. If it's a strong acid or a strong base, you will break it apart. What doesn't get broken down in net ionics? Solids, liquid, gases, or weak acid or bases, even if they say aqueous. There we go. So in that last problem, we had a weak acid. We left it together, pretending it was like a solid, liquid, or a gas. Here are the strong acids. So these are the ones that you would break down in net ionic equations, honors. Hydrochloric, hydrobromic, hydroiodic, nitric, sulfuric, chloric, perchloric, sulfuric, and phosphoric. So those are your strong acids. Strong bases are the group 1A hydroxide, so I'm talking about the first column on the periodic table bonded with the hydroxide. So lithium, sodium, potassium, rubidium, and cesium. And then the other kind of group of strong bases are the second column, group 2A with hydroxide, but just the heavy ones, so calcium down, so calcium, strontium, and barium. So now we looked at neutralization, right? An acid plus a base makes water and sometimes another piece. Now let's look at dissociation reactions. So this idea, even though regular chem, you don't need to do net ionic equations, this is very important. When you have a strong acid, or a strong base, so from the list, only the ones from the list we just looked at, and you put it in water, those strong things will dissociate 100%, or another word is ionize. So here's what I mean. Let me try to zoom in. Here's HCl. Whoa, make you dizzy. Here's HCl. So we got little bitty H pluses and little bitty Cl's, right? If I put that in water, here's my Mickey Mouse H2O. Look what happens. When it goes into the water, we make Cl minus, so chlorine with a minus charge. Look at all of those. And this weird new thing called H3O plus, and I think it's over on this side. Let's see. Maybe not. So this guy is H3O plus. This is called hydronium. and it is the same as H plus. So essentially, when I say they dissociate 100%, we are 100% breaking up into H plus and Cl minus, and I'll show you how these are the same in a second. A weak acid, so HF was not on our list of strong acids. Look at what happens when I put HF in water. So now the little blue is hydrogen, the gray is fluorine. When I put it in my Mickey Mouse, look at most of the acid stays the same. Sure, there are a couple, a tiny one right here, a tiny one right here, a little hydronium, but for the most part, it stays as HF, whereas the strong acid, it split apart. So here's how we write dissociation reactions. Let's do acids first. We take our acid, HCl, plus H2O liquid, and it is going to make, so we know acids donate H pluses, right? So it's going to donate this H plus to form H3O plus, and then what's left over? Cl minus. How else could I write this? Because it says usually we don't write the water. Well, for a dissociation, instead, because we know H3O plus is the same as H plus, a lot of times what we do is we say HCl will break down, and I'm actually going to use two-way arrows. Honors chem, you know what that is. Regular chem, don't stress about it. It's going to break down into H plus aqueous plus Cl minus aqueous. Why am I allowed to omit this H2O and use H plus instead? Well, remember what aqueous means. Aqueous means dissolved in water. So it's kind of repetitive to say solid HCl plus liquid makes aqueous aqueous. We can just, because of these aqueous symbols here, assume that we dissolved it in water, that water is involved. So here's another example. HBr will break down into Br minus and H plus. Both are aqueous. HNO3 will break down into H plus and NO3 minus, both aqueous. So those are dissociation reactions. Super easy, right? We're just breaking apart because we know strong acids, when we put them in water, they split up into their ions. What about bases? What do those look like? Bases are very, very similar. Here's a base, NaOH. It's going to break apart into OH minus and Na plus. And here's another example. Ooh, interesting. So BaOH2. So when we crisscross barium with hydroxide, there's a 2. Well, what's this going to break into? 3 things now. It's going to break into the barium 2 plus, right? That's this piece. And it's going to break into the OH minus, but there are 2 OH minuses, so we put a big 2 in front. These reactions should still be kind of balanced, right? 2 O's on this side, 2 H's, 2 O's, 2 H's. Okay, so those are dissociation reactions. So for these 6, I would like you to pause the video. This is the last slide. Pause the video, and you're going to tell me first, are they an acid or a base? So does it look like something that can donate a proton? Does it look like something that would accept? Here's the clue. Look for an H out in front. Look for not an H out in front. And then write the reaction, the dissociation of how they break up in water. So I'm going to pause the video, and then, or you're going to pause the video, and then I'll put up the answers for you to check in 3, 2, 1. So here are your answers. The red are my acids. How did I know? They had that H out in front. That's the proton that can be donated. And there's 2 ways you can write these. You can have the acid breaking into the positive H plus and the negative whatever else the ion is, right? So this would be I minus. This one had a polyatomic, so H plus and then ClO4 minus. H plus and then C2H3O2 minus, or you could have mixed it with water, right? And it would have made H3O plus and then the I minus. Again, we know water can be omitted, and then H3O plus is just the same thing as H plus. Bases, same idea, splitting into, whoop, let me fix something. This should be 2. I forgot to balance because of that 2, and the other ones are okay. So hopefully you got those right, and I hope this helped. Post on the discussion board if you have any questions.